The next integration technique we're going to learn is partial fractions. So to take the derivative of a rational function, which is just one polynomial divided by another, we would use the quotient rule, okay? And hopefully you have a vague memory of the quotient rule involving a fraction. The method of partial fractions is a technique for integrating rational functions, so undoing the quotient rule. We rewrite the given rational function as a sum of simpler rational functions and then anti-differentiate the terms separately. And in order to get through this, there are two integral formulas that you're going to want to keep in the back of your mind, and that's these here. And the reason these in particular are relevant is because each of them has to do with the integral of a rational function. The integral of 1 over x dx is the natural log of x plus c, and 1 divided by x squared plus 1, that integral is the inverse tangent of x plus c. So before we introduce the whole method in integration, we need to practice some fraction skills here to make sure that you are able to get common denominators and to lay the groundwork to understand the method. So I modified example 1 slightly from your book. And I'm asking you, first of all, to verify that this statement is true, that 2 over 1 minus x squared is the same as these two separate fractions. And then use that to actually integrate that rational function. So step 1 is just to prove that that relationship is true. So I'm going to start with the right-hand side, the two separate fractions, and combine them back together to show that I get the left-hand side. Now, in order to add fractions, if the denominators are different, you need to find the common denominator. And when you're working with binomials like this, very often your common denominator just ends up being those two binomial factors side by side. So if that's going to be my common denominator, what I need to do then is change each fraction to have that denominator. So with the first fraction, it has the 1 plus x factor. It's missing the 1 minus x on the bottom. So I want to multiply the bottom by 1 minus x. But to keep the fraction equivalent to the original, I need to do that to the numerator as well. The other fraction is missing the 1 plus x on the bottom. If I want to keep the fraction equivalent to the original, I'm going to need to multiply the numerator by that same factor. So 1 minus x times 1 is just going to be 1 minus x plus 1 times 1 plus x is just going to be 1 plus x. Now all over my common denominator, you can see how the x's are going to drop out. And I get 2 over 1 plus x times 1 minus x. And when I go and look at my original statement here, I only have a binomial instead of a product of two binomials. So I'm going to go ahead and just multiply those out using FOIL, distributive property, however you want to think about it. I'm going to do 1 times 1, 1 times minus x. Then I'm going to do x times 1, and then x times a negative x, which gives me a negative x squared. Middle terms drop out, and I do get what we were hoping to establish, which is that the two separate fractions are the same as 2 over 1 minus x squared. So I've established that this relationship is true. Now watch how that helps us with this integration. Since I know that this fraction that I want to integrate can be thought of instead as two separate fractions being added together, namely 1 over 1 plus x dx plus the integral for 1 over 1 minus x dx. These are now things that are simpler to integrate. Now, again, part of this is, you don't know what technique to use. if you try to use u substitution on this original and let your u be the bottom part of your function, you can see how your du would become negative 2x dx. And while that's close to what we have here, we're missing that x. We're off by that factor of x and the negative sign. So u substitution, we could try going further with it, try to get that x by itself, replace that, see what the integral turns into. But instead, these integrals are much easier to proceed with u substitution because now look, I've just got my u for the first integral is going to be 1 plus x. My du is just going to be dx, so that's fantastic. For my second integral, I'm going to switch to v here, and don't get confused and think I'm doing integration by parts. I'm doing u substitution, but I don't want to use u again for a different integral. So I'm using v and letting that be my denominator, and then finding my dv, which will be negative 1 dx. And I can move this constant over to the other side, so negative 1 dv equals my dx. I can rewrite these integrals now using those substitutions. So the first integral becomes 1 over u du. The next integral, we just have to be careful. The dx has to become a negative 1 dv, so this will become minus the integral of 1 over v dv. And using the rule up above, we know that each of these is going to turn into a natural logarithm. So we're going to get natural log of the absolute value of u minus natural log of the absolute value of v plus our constant. And now I substitute u and v back. So I get 1 plus x in my first absolute value sign, and I get 1 minus x in the second one. And that was a fairly simple integration to do. So the idea behind partial fractions is if there's a convenient equivalent way to express the fraction as a sum or possibly a difference of other fractions, those other fractions very often are simpler and we can integrate them one at a time. Now, how you figure out how to rewrite your fraction is another matter. So that's why I said we're kind of doing this baby steps. So let's take a look at modified example 2 here. I'm telling you that this mess is equal to the sum of these 3 separate fractions. So first I want you to verify that that relationship is true, and then use that fact to integrate to get this integral here. So again, I'm going to begin on the side with the separate fractions. And I'm again going to want to go about getting a common denominator. Now the common denominator, in this case, I'm just going to take each of these individual denominators and line them up together. Now, just like before, I'm going to go back to each of the fractions on the left and figure out which parts of that common denominator they're missing. So the first fraction has the x. It's missing 1 plus x squared and x plus 2 on the bottom. So that's what I'm going to want to multiply the top and bottom of that fraction by. The middle fraction has the middle factor in its denominator. It's missing the x and the x plus 2. So that's what I'm going to multiply this one by. Top and bottom. And the last fraction has the last factor. It's missing the first 2. So I'm going to need to multiply top and bottom by x times 1 plus x squared. All right, now getting through the rest of this is just algebra. But again, if you haven't done this stuff in a while, this is why I think it's worth going through a couple of examples of just the algebraic part before worrying about the integration. So if I do 1 plus x squared times x plus 2 times 1, okay, 1 times anything is just that stuff. So I'm going to just write 1 plus x squared times x plus 2. I'm not going to bother multiplying that out all at once. Then I have a plus sign. Now I have a 1 times this stuff. So I'm going to have x times x plus 2, which I need to multiply together. I'm going to have to make my fraction bigger. And the last part I have lined up next to each other, a 2 times an x times a 1 plus x squared. So I'm just going to do that. 2 times x times a 1 plus x squared. All right, now it's time for the algebra fun. So we're going to need to use FOIL, again, double distribution, to multiply the first two binomials together. So that's just the first component of the numerator multiplied out. Now I use distributive property on the middle to get x squared plus 2x. And then last part, I need to multiply 2x times 1 and 2x times x squared, giving me 2x plus 2x cubed. And the only reason I'm keeping those in parentheses is so that you can see the first chunk of the numerator became this, the second chunk of the numerator became this, the third chunk of the numerator became this. And of course, that's still all over my common denominator of x, 1 plus x squared, x plus 2. Now I'm going to go through my numerator and combine like terms. So I'm going to start with my highest degree. I like to put things in order with highest degree first. You can see they actually did it backwards in what we're trying to verify. Either way, doesn't matter. But I do have an x cubed here and an x cubed here. So when I combine 1x cubed with 2x cubed, I do get 3x cubed. So that's a match. Next, I'm going to look for something else I can combine. I've got 2x squareds plus another x squared. So that's going to be 3x squareds. And that is also a match for what I'm trying to verify. Then I go and look for my x's. I have 1x plus 2x's is 3x's plus 2 more x's is 5x's. And the last one, I've got this plus 2 constant that's going to go here. Okay, so this is, again, just a lot of algebraic work that you may or may not have done recently. But now that we have verified that these three separate fractions are equivalent to this monster fraction, again, watch how easy this makes the integration process. So instead of having to integrate this, I can now integrate three separate integrals that are going to be simpler. So I begin with the first one, 1 over x. I actually can just straight up say, oh, hey, that's natural log of x, plus a constant. I'll throw the constant on at the very end. And then when I look at the next portion, I may be tempted to say, okay, well, I'm going to let my u be the denominator. I'm going to take the derivative of u, and I'm going to get 2x dx. And again, when I kind of look at what I'm given here, I don't have an x in the numerator. So u substitution is going to run into a problem. And again, this is where you kind of have to stop and say, okay, what else is there? And if you go back to my opening here, I reminded you that 1 over x squared plus 1 is a unique integral. It becomes the inverse tangent of x. So at this point, even if you were in the zone and thinking just basic u substitution, once you run into a problem, take a step back, look at the big picture, and in fact, this is just inverse tangent of x. Now this last one, I would take off to the side, and again, I would try my u substitution on the denominator. Here I'm happy because it's just an x, so the du is going to be dx, so this is a great candidate for that u substitution. I'm going to pull my constant out in front, so I'm left with the fraction 1 over u with a du. And then from here, this becomes the natural log of u. I'm going to put my plus c in now that I have finished all of my integrals. And when I put u back in, I'm going to replace it with x plus 2, giving me a final answer of natural log of absolute value of x plus the inverse tangent of x plus 2 times the natural log of x plus 2 plus c. And that would be my final answer. So you can see that partial fractions is helpful. The big leap, though, is how do you know to turn this monster on the left into these particular 3 separate fractions? Well, you can see how we've just kind of pulled the denominator apart, but knowing what numerators you need at this point should seem like a mystery. So we're going to break that down next. It turns out that every rational function does have an elementary antiderivative, which involves only logs or inverse tangents and rational functions. So the hardest problem is that algebra of rewriting your rational function as a sum of partial fractions. So there are 3 things that are true that make this method work. And again, I'm not going to go through and prove the method. You can see your textbook for more details. But what it boils down to is these 3 facts. Number 1, every polynomial can be written as a product of linear and quadratic factors. Okay, every polynomial. Second fact, linear factors are automatically irreducible. You can't further factor them, in other words, because it's just an x to the first power. If it's a linear factor, you're not going to be able to factor anything out of that. Quadratic factors, things that have an x squared in them, may or may not be reducible. Okay, they may or may not have linear factors. So we're going to keep that fact in mind. And proper fractions. A proper rational function is when your degree of your numerator is smaller than the degree of the denominator. Okay, so your highest exponent is going to appear in the bottom part of the fraction. Any proper rational function can be written as a sum of proper partial fractions. So this method in particular, we've got to make sure we have a proper fraction. All right, so putting these facts together, here we go with the method of integrating rational functions by partial fractions. If your rational function is improper, so if your numerator has a higher degree than your denominator, you're going to have to use long division, polynomial long division, to rewrite the function as the sum of a polynomial and a proper rational function. Now, what I'll probably end up doing here is posting a separate video to teach long division if you don't remember it. I am going to do examples with long division, which should be enough for those of you who have seen it before, but I would encourage those of you who haven't to watch the tutorial video I post on that. If your fraction is proper to start, then here, this table tells you what form the partial fraction form is going to take. And there's different scenarios here. So you can see in case 1, doesn't matter what your numerator is, but if you have linear factors, which are x's to the first power only in your denominator, then your partial fraction form will be split those up. You will have a constant numerator, but anything with only linear factors in the denominator is going to be able to be written this way. If you have repeated linear factors in the bottom, so instead of having 2 different ones, you might have ax plus b, in this case, 3 times. You will always be able to find a partial fraction form where you write out those powers. So you write out an ax plus b, and that obviously is to the first power. And then you make another fraction where you do ax plus b, but to the second power. And then you do ax plus b to the third power. And again, you keep constants in the numerator. So when you have linear factors of either type, your numerator of your partial fractions will be constants. Now, remember from the first fact up here that every polynomial can be written as a product of linear and quadratic factors. So these first two cases handle the linear factors. Now, if you get a quadratic factor as your denominator, an x squared, and it's irreducible, meaning it's impossible to factor this quadratic, you can get the partial fraction form this way, by just keeping that denominator and putting a linear expression in the numerator. So you're going to have an ax plus a constant. If that quadratic irreducible factor repeats, if you get multiple of them, you handle it the same way you handled the repeated linear factors, where you're first going to write that irreducible quadratic to the first power, then you're going to write it to the second power, and again, when it's a quadratic, you always put something linear in the numerator. So we're going to have ax plus b as my one numerator and cx plus d as my other. Now, if you're quadratic, you can reduce the factors. Remember, that means you can factor it into linear factors. And so you end up back up here as a case 1 or a case 2. So this is how you handle the quadratics you can't reduce. So this is the groundwork now for how you will go about determining the partial fraction form for a rational expression. In the next video, we'll go through and perform this partial fraction decomposition. And again, before jumping in, if you've never seen polynomial long division before, please take the time to look at the tutorial video.